Okay, so hey guys, how's it going? So today I'm going to be going through a little presentation that I put together on exposure and exposure rate. I have 10 questions that I've gathered. Now, I've decided to create an entire presentation on exposure and exposure rate, primarily because I think that addicts doesn't really spend a whole lot of time with these two concepts, and I think there's a lot of popular questions out there that are commonly asked. But also, I'm probably also going to be making a lecture on fluence rate, and energy fluence, and energy fluence rate separately by itself. I may incorporate charge particle equilibrium and radiation equilibrium within that PowerPoint, or I may even create a PowerPoint by itself for CPE and RA. But with that, so I have 10 problems to work through today. Also, it's very, very warm where I am, so I'll be drinking a lot of water. So if you don't mind. Okay, so let's begin. So problem one. Start off with easy problems, work our way into more difficult. What is the unit of exposure? I've covered this in my other lectures. It is the Rankine. Convert 100 coulombs per kilogram to the unit of exposure. Okay, so 1 Rankine is equal to 2.58 times 10 to the negative 4 coulombs per kilogram. You should have that memorized, that conversion. So here's a conversion. And we get 3.88 times 10 to the 5th Rankines. Okay, so a point consisting of air is in an X-ray beam. Receives an exposure of 100 Rankines. So first off, what do you need to have to calculate dose? If you have exposure, what do you need to have to calculate dose? You need charge particle equilibrium. Here is the relationship, just in case you're wondering. This would be a good relationship to write down on your formula sheets. If you followed through with my, and you watched my video on 10 tips for new medical physics graduate students who are just entering into a program, this would definitely be a relationship to write down. Okay, so notice that so part B, what is the collision kerma? So notice that you don't need CPE to convert from collision kerma to exposure. You do not need that, but you do need the W over E, which is a constant. That is 33.97 joules per coulombs. Okay, so what is the collision kerma? Let's calculate that. In case you didn't know, units of collision kerma are going to be in joules per kilogram, which is also dose. So absorbed dose is in gray, joules per kilogram. Collision kerma in kerma, also gray, joules per kilogram. Okay, so let's do the conversion. We have 100 Rankines, so we're just going to convert from Rankines. 2.58 times 10 to the negative 4 coulombs per kilogram. And we will multiply that by our W over E to get the units we want, which are joules per kilogram. Okay, so question C. Okay, so now what would the value of dose be? If we have collision kerma, what is the value of dose? And let's say we have CP, charge particle equilibrium. They're the same. So as you can see from that relationship, dose and air is equal to collision kerma if you have CP. So important to recognize that relationship. Okay, so moving on to problem 3. So yeah, I feel that ADDX does not spend a good enough amount of time on exposure rate constant. I think it's very important. So right off the bat, what is the formula for exposure rate constant? Notice that the distance from the source is squared. That is a numerator. The activity, not squared, denominator, and then exposure rate. Sometimes people call it gamma, but you can confuse, gamma it's used a lot in this field, so you can sometimes confuse it with other things. So I almost prefer saying exposure rate constant. Okay, here's a good one. What are the units for exposure rate constant? There's actually two that are acceptable. So it would depend on the question. The question, if you had to solve for exposure rate constant, they're probably going to say which units they want. You're going to be solving for those units. So there they are. Okay, so now a calculation. Okay, so let's say you have a point source of 2 millicurie. It has a gamma or exposure rate constant. 2 Rankins per centimeter squared over millicurie per hour at a distance of 2 centimeters. What is the exposure rate? Okay, so here you're basically just rearranging the formula. So you have your distance, you have your activity, you have your gamma. So just calculate your exposure rate with the formula given in A. Okay, so you should get a value of 1 Rankine per hour. Nothing too difficult there. Just a simple rearranging of the formula. Okay, so let's start getting into concepts that could actually be lead to some tricky questions. Okay, so what do you need to calculate fluence rate? What do you need? What quantities do you need? Calculate fluence rate. So you're going to need the activity in disintegrations per second, which happens to be the definition of Becquerel, and you're going to need distance from the source. So the fluence rate, typically the formula for if you're calculating the fluence rate from a source, it's activity over 4 pi r squared. The 4 pi comes from, I mean, hopefully you guys cover this in your lecture, and then you work through my problems after that. It's a unit of solid angle. It's when you integrate over all angles, you'll find that the unit of solid angle is 4 pi. So when you're looking at basically if you have a source, it doesn't follow like a direct inverse square because you have a volume source. It goes by 4 pi r squared. It decreased by 4 pi r squared. So that's what you need to incorporate that into your fluence rate calculation if you do have a radioactive source. So let's say we want to calculate fluence rate from an activity of 1 curie at a 2 centimeter distance from the source. How would you do that? So you just use that formula. You put in 1 curie for activity, but you have to convert to disintegrations per second, which is the conversion for Becquerel, and at 2 centimeter distance. So it's 4 pi 2 centimeters squared. And you get your answer of 7.36 times 10 to the 8th centimeters to the negative 2 or times seconds to the negative 1. Okay, problem 5. So from exposure rate, energy, activity, and distance from a source, how do you calculate the mass energy absorption coefficient of air? This could very well be a question that could be on one of your tests. So, okay, so exposure rate is equal to, it's collision kerma over your W over E value. And then because we say exposure rate, we also have to multiply it by 1 over time. Okay, let's break down that collision kerma into even more components. So now we have the collision kerma turns into, that's the energy fluence. I know it looks a little funny, the symbol, that's the font of it. That is the energy fluence. Now that term right there is the mass energy absorption coefficient. You can look that up in tables and ADDICS. Okay, so I decided, oh, okay, now you can break down the energy fluence. And now here's the tricky thing, because we said exposure rate, so now we have time. So really, you could break down energy fluence into energy and fluence. Now, because we want time, its exposure rate, we can say fluence rate. And then same, multiply it by mu n over rho, W divided by W over E. Okay, now we can rearrange. So now we're going to rearrange for the mass energy absorption coefficient of air, and that's how we get it. Notice it's in centimeters squared per gram. Hopefully you guys can all see this mouse. This should also be multiplied by 1 over time. So just so it works out. So yeah, that's another formula. You're going to want to write it down on your formula sheet. Okay, so for problem 6, let's break it down into where you're actually solving a problem with all the quantities. So you have 10 MeV energy, 2 Curie activity, 10 centimeters from the source. The mu En over rho is 0.0145 centimeters squared over grams, so it gives us it. What is the exposure rate? Let's do it in coulombs per kilogram per second. So as we just learned, exposure rate is energy times fluence rate times mu En over rho times W over E. So we can plug them in now, which is nice. Let's plug in the values. And we know our fluence rate is activity in disintegrations per second over 4 pi r squared. So we have, let's calculate fluence rate first, just so things are neat. We have 2 Curie times 3.7 times 10 to the 10 disintegrations per second over Curie divided by 4 pi r squared. Our case was 10 centimeters. We get our value. Okay, now let's put it all together. Very nice calculation here. So let's put all the values in with the unit conversion. So you see a nice calculation. So 10 MeV was given. The conversion to joules now. Okay, so joules over MeV. We have centimeters squared over gram, which is the mu En over rho. We have that conversion to kilograms. That's our value, the 5.9. That's our value from fluence rate, and we're going to divide it all by W over E. We get our final value. It's going to be coulombs per kilogram per second. But it's not in Rankins. That's I said don't put it in Rankins. Just do coulombs per kilogram per second. Okay. Now, let's convert it to Rankins per hour just for fun. Okay, that last solution. So our solution was 4.03 times 10 to the negative 5 coulombs per kilogram per second. Let's convert it to Rankins per hour. So we just have our initial conversion for Rankins, 2.58 times 10 to the negative 4 coulombs per kilogram. And then we're going to do just our time conversion. So 1 over seconds, we want it in hours, multiplied by 3,600. We get 562.3 Rankins per hour. Okay, let's go to problem 8. Now, from the exposure rate calculation in the last question, let's put it all together. Let's calculate the exposure rate constant with activity of 2 curie, distance from the source 10 centimeters. Okay, there's our formula. Let's put it in Rankins per hour, a centimeter squared over millicurie. Let's put it in those units. So here was our answer, 562.3 Rankins per hour. And then let's just do our calculation. But we do have to convert curie to millicurie. So there's our conversion. 1 curie is 1,000 millicurie. And then we just multiply it out. We get 20.12 Rankins per centimeter squared per millicurie per hour. We could have also calculated it with the other units. It doesn't matter. For our question, we decided to go with these ones. Okay. So question 9. We're going to do some inverse square calculations just for practice. I think we did a good job with the exposure rate constant. Okay, so problem 9. What's the formula for inverse square law? Okay, so intensity 1, that's your initial. Distance 1, that's your initial. So intensity 2, that's your not your initial, so your secondary. And distance 2, same idea. Okay, something that might come up is, isn't it kind of intuitive? Why do you need a formula? The reason why it's good to actually have this formula written down and you know it off the top of your head is because a lot of the times when you're working through calculations, there may be a time limit, or you may be under pressure, like for example on the ABR board exam, or your exams in your course. So sometimes it's good to just keep things very simple for that reason. If there's a time limit and you got to work really fast, you just want to kind of plug and chug in this case. So that's the formula. So for B, for a point source, the exposure rate is 100 Rankins per hour at 50 centimeters. What is the exposure rate at 2 meters? I know this off the top of my head because, so that's what it is at 50 centimeters. So what is it going to be at 200 centimeters? So that's 4 times the distance. Inverse square, it's going to be 1 over 16. But let's do the calculation. Okay, 100 Rankins per hour, which is your initial exposure rate, over the secondary, equals the secondary distance, which is 200 centimeters over 50 centimeters squared. Let's work it out. 100 Rankins per hour over your secondary equals 16. Rearrange, and we get our answer 6.25 Rankins per hour, which is, it's 100 Rankins per hour divided by 16. So 4 times the distance that I know inverse square. So that's, I would know 16 off the bat. But sometimes it's good if you're in a crunch, racing the clock. It's good to work it through. You don't, you don't want to leave room for mistakes. Okay, and the final problem, which is also an inverse square problem, but a little bit more going on. So the problem is, how long will it take in hours for a source emitting 100 milliroentgens per second at 25 centimeters to accumulate a total of 100 milliroentgens traveling a distance of 50 centimeters through a 2 centimeter thick material that reduces the exposure by 2 half valulars. Notice that we don't care about the thickness of the material because I said that it reduces it by 2 half valulars. So let's work through the problem. Inverse square law first. Okay, we have 100 milliroentgens per second. We have our final distance and our initial distance. Put it in. Okay, calculate it. And we get 25 milliroentgens per second. Okay. So now we're going to have to factor in these 2 half valulars. So we're going to multiply it by 2 half valulars. Half valvular means one half valvular means you reduce the intensity by 1/2. So you can go by 0.5 for each one. So nothing too fancy there. We get our answer of 6.25 milliroentgens per second. Okay, now we want to know how long it'll take to accumulate a total of 100 milliroentgens. So here we know 6.25 milliroentgens per second. We're going to take 100 milliroentgens divided by 6.25 milliroentgens per second. We get our answer of 16 seconds. Nice, very nice problem that allows you to just sort of problem solve and just give you more, more opportunity, I suppose, to perform some problem solving and work with inverse square law. You'll definitely see problems like this within your program. Okay, so that was 10 problems on exposure and exposure rate. Yeah, thank you very much. I think I had some very excellent problems. We spent quite a bit of time on exposure rate constant, exposure rate, and also introduced the inverse square law. I believe the examples are very good, the ones that I selected. I don't think you should have any problems working through any of the problems in ADDX, but I don't believe there might be 1 or 2 on the exposure rate constant in ADDX. Not many, unfortunately, and that is a common problem I think in your program, and they're popular questions. Okay, so that's all. So as always, thank you very much for viewing, and good luck studying.